All right. Hello, everybody. My name is Avra, and I've been working with Kristen. And we've been working with the Rhymorphous Initiative with Dr. Toby Minar to understand how much water makes a flood. And so we're exploring the relationship between river gauge data and flood extent. So the overarching premise of our project is to understand how water floods. And to start, I want to emphasize that we're positioned within this Rhymorphous project, which is also known as the River Morphology Information System. And it's an NSF-funded cross-institutional project that aims to provide an application to aid in river morphology research. So using data to describe, the shapes of river channels and how they change in shape and direction over time. So Rhymorphous is really trying to extract insights about river morphology using a variety of parameters, like the diagram on the screen shows. River morphology is multidimensional, so to properly understand it, we need inputs from surface topography, water volume, water area, and point and line topologies. And so mine and Kristen's role in this larger project is to look specifically at the intersection of water volume and water area to better understand flooding. And we're helping to develop a tool that will extract river geometry during flood events to compare water area and water volume. This kind of tool can help aid in flood modeling and mapping so we can better understand flood events based on current data-driven observations and not just historical events. And it can also help us better understand river bank and river channel migrations, like how river banks change over time or which channels in the US are moving consistently with time. So this is important because, well, there's actually a really recent example that I think contextualizes this problem well. I'm sure most of you are familiar with it, but earlier this month, Montana and Idaho and Washington all had extraordinary floods due to a very wet spring. In particular, Red Lodge, Montana experienced a 500-year flood that ripped out houses and vehicle bridges. And so modeling flooding and understanding where water goes can help us make informed decisions about how we build our infrastructure. So it can answer questions like, should we go through the extra time and money to build bridges that can withstand the next 500-year flood, or simply put a new one in and accept that it's probably going to be broken down again with the next historic flood? This is also useful in knowing where the water goes in relation to how much water is flooding, because it can help us mitigate hazards with critical habitats and agricultural land. And lastly, riverbeds are essentially conduits for sediment, so we can learn about how sediment is transported through watersheds before, during, and after flood events. All right, so our project goal was to visualize river geometry by plotting water area against water volume, right? So we can gather the data for water volume by utilizing data provided by the USGS as they measure water levels at more than 10,000 gauges throughout the US. We can gather the data for water area by using aerial imagery provided by satellites and extracting how much water covers the land in those images. So the quick summary of our methods is first to get the right site. And some of the criteria for that is that it has a flood event over a period of time. It also has either stream discharge or gauge height data from the USGS. And just a quick note on gauge height and stream discharge, for those of you who aren't familiar, gauge height is the height of the water level, and stream discharge uses gauge height to evaluate the rate at which a volume of water passes by. So some sites provide both pieces of information, some sites don't. So we did our analysis comparing both of those parameters. And the last criteria needed is satellite images that can actually see through the ground during flood events, because as you can imagine, flood events often happen when there's high precipitation and cloud coverage, which can affect how well satellites can produce clear images of the ground. So once we selected our sites, we completed analyses on both the satellite imagery and the hydro data. For the hydro data, we extracted the maximum hydro value per month for the flood event time period. And for the satellite imagery, we filtered out all the clouds we could, classified the water using the normalized difference water index, which allows a body of water to stand out against soil and vegetation, and then counted the number of water pixels extracted. So the higher number of water pixels, the more area the water covers. And then lastly, we plotted the number of water pixels against the max hydro value over the flooding time period. This is kind of what some of the data looks like when it comes from the USGS. And here's one specific site that we picked, Vicksburg, Mississippi, where the stream gauge is in a specific location in the river, and we can extract the gauge height as well as the discharge in cubic feet per second. This is what the satellite analysis looks like. So this is what the natural imagery looks like when it's extracted from Sentinel-2. And then this next image is what the NDWI image looks like, which helps extract where the edge of water is. And we can see how it changes over time from the dry season to the wet season and visualize how channels and banks change. And finally, we can extract the water extent and count the number of water pixels in a given image, which helps inform how much of the area the water covers.
Thank you, Ava. So as Ava said, that was our first site on the Mississippi River at Vicksburg. Our other site we decided to analyze was in Pine Bluff, Arkansas, on the Arkansas River. Here's the true color image where we're looking at. And as Ava mentioned, we then generated NDWI images from those remote sensing data. And one thing you'll notice here is that we used different boundary conditions for this site, and I'll touch more on this a little bit later, but we found that we were able to get more accurate water pixel counts that actually represented the flooding of the river versus anything that was going on outside of the river. And so this is the dry season NDWI image, and there is a flooding event at the same location, which we then can convert to this kind of water map where we can extract a water pixel count. And see what kind of extent we were looking at. And here are the results that we ultimately got. What we're looking at here, what these plots show is water pixel count on the y-axis that represents the flooding extent or the amount of land surface that was covered by flooding water. And on the x-axis, we have our stream gauge data. So on the left-hand side, that is for the Mississippi River at Vicksburg. Here, we decided to use gauge discharge data because that's actually the only data that was available for that particular site. That's measured in cubic feet per second. And on the right-hand side, with the blue dots, we're seeing the Arkansas River at Pine Bluff site. This is water pixel count versus the max month gauge height data. Again, that's the only data that was available for this particular site and the USGS site. What we would expect to see, and Ava touched on this earlier, is that if we plot water pixel count versus stream gauge data during, business as usual day-to-day river operations, we wouldn't expect to see any increase in water pixel count during the lower end of the discharge or gauge height values. But once we hit a certain threshold value and flooding starts to occur and water starts flowing over the banks, we would expect that the water pixel count would start to rapidly increase with each increase in discharge or gauge height. As you can see, we saw this relationship much more clearly at the Mississippi River site. And I'll touch on why we think that is in a little bit, but here we can see that during these low discharge values, we're seeing really not any substantial increase in water pixel count. And then once we hit a certain value, we start seeing rapid increases where we're seeing a lot of water flooding the surrounding areas. One thing that I do want to note here is that what we would expect, as Ava said, during the methodology, we have a maximum month discharge or gauge height value, and then we have a water pixel count value for each month. So we would expect 12 different values over the course of 1 year. Both of these take place in 2019. But what we ended up having to do because of cloud coverage was omitting certain data points. So you don't see all of the data points here because we had to omit the months for which we could not get a pixel count value because there was just too much cloud coverage at the time that remote sensing data was collected. And then also we'll touch on what we think this means in our conclusion slide. I'll just go there now. The first thing that we kind of established here was that we've established a proof of concept. We know that we can take images of remote sensing data, we can generate water pixel counts from each of them, and we can plot that against stream gauge data at that same location and see what kind of relationship we can get. We can't mathematically define that relationship quite yet unless we do more analysis at different sites and different locations, different flood events, to really kind of hone in on what that relationship is. And related to that, it looks visually, it would appear that the correlation between flood extent and discharge is stronger than the correlation between flood extent and gauge height. This, again, we would need further analysis at different locations and times, and at the same locations at different times, in order to kind of verify that hunch. But this intuitively does make sense. When you think about what discharge represents, it is not only incorporating the gauge height or the depth of the river at a certain gauge location, but also the volume of water that is traveling through that point. And so it would make sense that the flooding extent is more closely related to the volume of water that's passing through that point rather than just the gauge height. Next, we also learned during this analysis that we were hoping to make it iterable easily for each different gauge location in the US. But what we found is that sometimes, as for the Pine Bluff site, we're going to need to create specific boundary conditions for each location, because often, there are other bodies of water, there are fields that are being flooded with water, that's going to affect the accuracy of our water pixel counts unless we really hone in those boundaries to cover just the river and its surrounding banks. And then lastly, we learned that because of the cloud coverage issue, it might be beneficial for this analysis to consider using other active remote sensing data, such as Sentinel-1, something that has radar capabilities, so that we can kind of circumvent the cloud coverage issue. All right, and then the next steps is addressing those uncertainty sources that I kind of talked about on the last slide, using active remote sensing data for cloud cover, extracting stream discharge data and not necessarily using gauge height or getting one from the other. And then also trying to address the boundary conditions so that we can be certain that our water pixel counts are accurate in counting what's only happening outside of the river. And then for composite images, instead of using Google Earth Engine, maybe generating images that are specific to each gauge data point. The implications of this project are that we can potentially combine this kind of modeling with cross-section or channel shape data to understand how flood events impact the river shape and morphology over time, and then potentially using machine learning to make this model predictive and understanding when do we think flooding is going to occur, when will it occur, and how can we plan for that appropriately. Thank you very much for listening, and pop any questions you have in the chat or feel free to reach out to Ava or I.